In today's class, we shall be looking at heat transfer mechanism under conduction. We will also look at heat transfer mechanism under convection and radiation, but specifically today we are looking at heat transfer mechanism under conduction. And of course, we know that conduction is a process whereby heat energy or thermal energy is transmitted through a material due to the difference in temperature. So whenever we are talking about conduction, it has to do with the transfer of energy through a material medium. Okay, so in this case, you can see the figure here. We have a medium, we have a point of high temperature. At this point on the medium is subjected to a high temperature, while this one is subjected to a low temperature. So you can see the arrow here indicating the direction of flow, and the flow is from where we have a high temperature or higher temperature to where we have a cold temperature, and the L here is the length of the material. So with this, we can come up with an expression for the rate of energy transfer by the conductor. So if we are to estimate the rate of energy transfer by the conductor, we use the expression P equals to KATH minus TC all over L. P equals to KATH minus TC all over L. Okay, so the P here represents the rate of energy transfer by the conductor or by the rod in consideration, and then K represents the thermal conductivity of the material used, then A is the area of the material, TH, where you have the high temperature, the value of the high temperature, TC, the value of the low temperature, and L represents the length of the material. If we consider the expression TH minus TC all over L, still in that expression, the ratio TH minus TC all over L, this simplifies the magnitude of the temperature gradient. So if you are to estimate the magnitude of the temperature gradient, we use that expression TH minus TC all over L. And this is the temperature difference per unit length. And this temperature difference per unit length is simply referred to as the magnitude of temperature gradient. Okay, let's look at the first example here. And it says that a styrofoam box used to keep drinks cold at a picnic has total walls of 80 meters square and wall thickness of 2 centimeters. It is filled with ice water and cans of Coca-Cola at 0 degrees Celsius. Option A. What is the rate of heat flow into the box if the temperature of the outside wall is 30 degrees Celsius? B. How much heat flow in 1 day? C. How much ice melts in 1 day? Take thermal conductivity of the styrofoam to be 0.01 watt per meter per Kelvin. 0.01 watt per meter per Kelvin. So this is supposed to be slash here. Okay, looking at this question here, the area is given. So looking at the unit m square, I've seen the area, and here we have the thickness. Of course, this would also represent length, and this is in centimeter, while this one is meter square. So we are going to convert this to meters by dividing by 100, and then we have the temperature of the box to be 0 degrees Celsius, and we are asked to, at the first option here, estimate the rate of heat flow into the box, and we are given the second temperature, which is where the hotter side of the environment, and this value is in degrees Celsius, 30 degrees Celsius. Of course, these temperatures will be converted to Kelvin. So let us list the quantities we have so that we go into solving of the problem. The area is given. The length was given as the thickness. The first temperature, Tc. Then we convert it by adding 273, and this will give us the equivalent value in Kelvin. Then TH, or here I use T2, still the same thing. TH, 30 degrees Celsius, convert it to Kelvin by adding 273. So we get the value 303 Kelvin. Okay, so we have come up with the expression. If you look at the question, it says what is the rate of heat flow into the box? So the rate of heat flow into the box, we're going to use the expression P equals to KATH minus TC all over L for the rate of heat flow. Then we have substituted the value of K, 0.01, which is given in the equation, area 0.8, and then high temperature TH 303, and then TC 273, and L we now replace 0.02. When we simplify this, we have 12 watts. 12 watts. Let's go back and check the second option. How much heat flow in 1 day? How much heat flow in 1 day? Heat flow in 1 day. You're going to use this expression Q equals to P times T. Q equals to P times T. Okay, so of course we know that T represents the time, the day. And of course 60 seconds make 1 minute, 60 minutes makes 1 hour, and if we multiply that again by 24 gives us the time in 1 day. So we already have the rate of heat flow here, which is P, and that is how we are going to get the T. See what I mean? T, the time for 1 day, 60 seconds times 60 minutes times 24 will give us 86,400 seconds. This time represents the time for the whole day, which we are going to multiply with the value we got for the rate of heat flow. Okay, so Q equals to 12 times 86,400. When we multiply these two, we get 1.04 times 10 to the power 6 joules of energy. The next one said, how much ice melts in 1 day? In this case, this problem comes, it talks about melting. So what will come into our mind is latent heat of melting, that expression, latent heat of fusion. Of course, you should recall that expression. Mass that melts in a day. We are going to use the expression Q equals to ml, where LF represents the latent heat of fusion of ice, and this is M, the mass of ice. We already have Q here, which is given by 1.04 times 10 to the power 6 joules. We are to find the mass, but latent heat of fusion is a constant. okay, which is of the order 3.34 times 10 to the power 5. And when we substitute that here, we will get what we are looking for. But making m the subject, from this expression we have q over lf. Then we substitute the values into that expression and we get the final answer. Thank you for watching. Have a blessed day. Please, if you have not subscribed to this channel, please encourage us by clicking on the subscription button and also share to your friends and relatives and well-wishers. Bye.